Hi, I'm Ronen Shaltiel, and I'm going to talk about hardness assumption needed for extreme high-end pseudo-random generators in fast derandomization, and this is joint work with Emanuele Viola. In 1997, Impagliazzo and Wigderson showed that BPP equals P, assuming certain complexity theoretic hardness assumptions. What they did is that they constructed high-end pseudo-random generators, and by that I mean pseudo-random generators that are optimal up to constant factors, based on assumptions that are necessary, at least up to constant factors. And it is well known that if you have such high-end pseudo-random generators, then BPP equals P, namely there exists a constant C, such that every randomized algorithm running in time M can be simulated deterministically in time M to the C, and this is wonderful. We all like this theory. Recently, motivated by fast derandomization, that is, trying to minimize this constant C, trying to show that the derandomization is as fast as possible, two beautiful papers, one by Doron, Moshkovitz, O, and Zuckerman, and the second one by Chen and Tell, construct extreme high-end pseudo-random generators. These are pseudo-random generators that are not only optimal up to constant factors, they are in fact optimizing the constants. These pseudo-random generators are optimal up to 1 plus minus below of 1 factors. And these constructions of pseudo-random generators are based on stronger hardness assumptions, and the assumptions are stronger both quantitatively and qualitatively. Now, quantitatively stronger assumptions are necessary in some sense because we're trying to get quantitatively stronger pseudo-random generators. But it's not at all clear that we need qualitatively stronger assumptions. So the question that we are addressing in this paper is it possible to show that if you take the original Impagliazzo-Wigderson assumption and properly scale it quantitatively, then you can get this assumption to imply that there exist extreme high-end pseudo-random generators, and we will be interested in whether there exist black box proofs achieving this goal. Okay, so are the new assumptions used by these two papers necessary? And to make a long story short, we don't know the answer to this question, but what we can do is we can rule out certain approaches, and our results show that the approaches of DMOS and of CT cannot yield such a black box proof, giving a partial justification of why they use stronger assumptions. So let me tell you about the Impagliazzo-Wigderson 97 theorem, and this is a setting that I call the high end. The theorem says that under a certain hardness assumption, which I'll call the high-end Impagliazzo-Wigderson hardness assumption, you get high-end pseudo-random generators. And let me spell out the definition of these things. So the high-end Impagliazzo-Wigderson hardness assumption says that there exists a function f on L bits such that f is not computable by circuits of size 2 to the omega of L, yet f can be computed by circuits of size 2 to the O of L, and I'll use T of f to denote the time to compute f on a single input, and T all of f to be the time that it takes to compute f on all inputs, on all 2 to the L inputs. And note that in the high end, if I require that T of f is 2 to the O of L, this is equivalent to requiring that if I require that T of f is 2 to the O of L, then this is equivalent to requiring that T all of f is 2 to the order of L because of its constant, right? But later on, these things will matter. So this is the high-end Impagliazzo-Wigderson hardness assumption. And the theorem says that it implies a high-end PRG. Namely, a pseudo-random generator which stretches a seed of length r, which is order of L, into an output of length m, where m is 2 to the omega of L. And this is a pseudo-random generator, meaning that it fools circuits of size m, more formally, that no circuits D of size m can distinguish between the output of a pseudo-random generator and the uniform distribution with probability larger than, say, 1 over 10, and some constant. And this PRG is high-end, optimal up to constant factors, because the seed length R is as small as possible, at least up to constant factor. The smallest possible seed length will be 1 times log m, and r is a constant times that, right? So this is what I mean by a high-end PRG. We also get that the pseudo-random generator runs in time 2 to the O of L, and once again, this is equivalent, because of the way the parameters are chosen, to saying that computing the pseudo-random generator on all seeds can be done in time 2 to the O of L. And when we have high-end pseudo-random generators, this implies that BPP equals P, namely that there exists a constant C, such that every randomized algorithm that runs in time m can be simulated by a deterministic algorithm that runs in time m to the C. And this is great. Let me make 2 comments. One is that the PRG G that is constructed in this theorem matches the PRG which is implied by the hardness assumption up to constant factors. And 2, that the high-end Impalliazzo-Wigderson on hardness assumption, this hardness assumption remains plausible even when we scale it by constants, even if we change the numbers here by constants. And this is why we can afford losing constant factors. Okay, so now we asked how small can this constant C be? We want faster derandomization. And we asked, what would happen if we had extreme high-end PRGs that are optimal not only up to constant factors, but also up to 1 plus minus little of 1 factors? So let's take a look at this setting, which I call the extreme high-end. And now, as I said earlier, this is no longer a theorem, it's an open problem. We would like to show that if you scale the Impalliazzo-Wigderson hardness assumption correctly, I'll call this stronger assumption the extreme high-end Impalliazzo-Wigderson hardness assumption, then you obtain an extreme high-end pseudo-random generator. And once again, let me spell these things out. So what is the extreme high-end Impalliazzo-Wigderson hardness assumption? Now we assume that there exists a function f on L bits, which is not computable by circuits of size 2 to the 1 minus little of 1 times L. So note that here we were allowing a constant, and here we want everything to be optimal, right? No, right? I mean, 2 to the 1 minus little of 1 times L is the largest lower bound that we can think about, because every function can be computed by a circuit of size 2 to the L. We also want to optimize the constants in the running time. And now what we want to optimize is the time it takes to compute f on all inputs. So we want to assume that f can be computed on all inputs in time something like 2 to the 2L, 2 to the 2 plus little over 1 times L. So this is the correct scaling, you should trust me on that, of the high-end Impalliazzo-Wigderson hardness assumption. And we want this to imply an extreme high-end PRG. So this is a pseudo-random generator where both the constants in the seed length and the output length are optimized. If here we had big O and big omega, now we replaced them by 1 plus little of 1 and 1 minus little of 1. We want a pseudo-random generator which stretches a seed of length 1 plus little of 1 times L bits into M, which is almost 2 to the L, 2 to the 1 minus little of 1 times L bits. And this is what an extreme high-end PRG, the seed length R is 1 plus little of 1 times log M, right? Optimal up to 1 plus little of 1 factors. And now we want that the time that it takes to compute G on all inputs, on all seeds, is roughly 2 to the 2L, 2 to the 2 plus little of 1 times L. And this is best possible because for this setting of parameters, there are 2 to the L seeds, and each one of them produces an output of length 2 to the L. So only outputting all these 2 to the L outputs already takes 2 to the 2L times, and we want the time that it takes to compute a pseudo-random generator G on all seeds to be almost that, 2 to the 2 plus little of 1 times L. Okay? So let me now compare this extreme high-end pseudo-random generator to the generator that I got earlier. So here, G needs to match the PRG that is implied by this hardness assumption up to 1 plus minus little of 1 factors, right? It needs to be much tighter than the previous pseudo-random generator. And this is because the assumption that we are assuming, the extreme high-end hardness assumption, becomes false when scaled by constant. We cannot take this 2 to the 1 minus little of 1 times f and scale it by constant, because every function is computable by a circuit of size 2 to L. Now, what kind of deterministic simulation do we get? It turns out that an extreme high-end PRG implies that C is something like 2 to the plus little of 1. So we get that every randomized algorithm that runs in time m can be computed by can be simulated by a deterministic algorithm that runs in time m to the c, where c is something like 2. And this is best possible because c cannot be smaller. There's a theorem by Carmosino et al. Showing that c has to be larger than 2 minus little over 1, assuming certain fine-grained complexity assumptions. So if extreme high-end pseudo-random generators give the best possible constant c up to this O of 1 factors, and it is an open problem whether we can construct them from the extreme high-end in Palliazzo-Wigderson hardness assumption. Now, before proceeding, I'd like to comment that if I ask this question, what is the smallest constant, in a slightly different way, so suppose that instead of measuring the time of a deterministic algorithm in terms of only the time of a randomized algorithm, but also in terms of the input length of the randomized algorithm, then it seems that the right answer is that every randomized algorithm that runs in time m of n can be simulated deterministically in time something like m of n times n, or m of n times n to the 1 plus little of 1. And this is follows from 2 beautiful papers of Chen and Tell, which I already mentioned. Okay, so now, on the left-hand side, we have a theorem. In the high end, we have a theorem, whereas in the extreme high end, we have an open problem. So can we use the techniques which are used to prove the Palliazzo-Wigderson theorem to solve the open problem in the extreme high end? So let's examine the techniques that are used in the high end. So in Palliazzo-Wigderson and later proofs, use a technique which I'll call a hardness amplification plus the hybrid argument. So they used the hybrid argument, and it turns out that this, as well as other issues in the proof, results in losses of constant factors. But losses of constant factors are not too bad in the high end because we can afford losses of constant factors. So this is why in the high end, we have a theorem. On the other hand, in the extreme high end, we cannot afford the losses of constant factors. So we cannot afford the losses incurred by hardness amplification plus the hybrid argument. We cannot afford these techniques. And this is why we have an open problem rather than a theorem. Nevertheless, as I said in the beginning, these 2 beautiful papers, the one by Doron, Moshkovitz, Owen, Zuckerman, and the second one by Chen and Tell, bypass this barrier, and they show how to construct extreme high-end pseudo-random generators, albeit assuming qualitatively stronger assumptions that I will now survey. Okay, so let's start with the first paper, the paper of Demos. And Demos say the following. We'll take a look at this open problem. We can make it a theorem if we strengthen the hardness assumption. So if instead of assuming that F is hard for standard circuits, we assume that F is not computable by circuits of size 2 to the 1 minus little of 1 times L circuits, but are stronger, but are also equipped with non-determinism and randomness. And this is a stronger assumption, but doesn't seem to be necessary in this setting. right? So this is the demos paper, and now let's take a look at the Chen and Tell paper. So Chen and Tell say, we take a look at this open problem, and we can make it a theorem if we throw in an additional assumption. And we now also assume, in addition to the extreme high-end in Palliazzo-Wigderson hardness assumption, we also assume that one-way functions exist. Now, once again, I'm not saying that one-way functions are implausible. Of course, they are plausible. I'm only saying that they don't seem to be necessary in this setting. Okay, so let's go back to the outline and see where we are. So I've told you what is the open problem I'm interested in. Namely, is it possible to show that the extreme high-end in Palliazzo-Wigderson hardness assumption implies extreme high-end pseudo-random generator? This was the open problem that I had on the previous slide. And since I'll be interested in showing negative results, improving limitations, I'll be interested in black box proofs. And the way I want to ask this question is there a black box proof showing this implication? And for this, I need to tell you what black box proofs are. So let's take a look at black box proof. So here I have the open problem that I'm studying. I'm asking whether you can take a function f and convert it into a pseudo-random generator G. And let me define what black box proofs are. And I'll start by saying that all known pseudo-random generator constructions have black box proofs in the following sense. A black box proof consists of two things. The first thing is a construction map. This is a map E, which takes a function f and convert it into a function G. I'll call it GF. So it takes a function f and it converts it into a function G. It can receive any function f, not necessarily a hard function. So where does the correctness comes in? The correctness comes in by the fact that we require that there exists a reduction, namely an oracle circuit R, such that for every function f and for every potential adversary D, not necessarily a small circuit, if D breaks the pseudo-randomness of GF, namely, if D distinguishes the output of GF from uniform, then when R receives oracle access to D, then it needs to compute F using few queries to the oracle D. Okay, together, these two things show that if F is hard, then G is pseudo-random. Why is that? Because if G is not pseudo-random, if there's a small circuit distinguishing the output of GF from uniform that is breaking GF, then since D is a small circuit and R makes few oracle queries to D, then R with oracle access to D is also a small circuit. And so, since R with oracle access to D computes F, and F is not hard. So we've just shown that if there exists a circuit D, a small circuit D, which breaks the pseudo-randomness of GF, then F is not hard, establishing the open problem, okay, with the right parameters. So now there's an asterisk here, because the actual definition of what is a reduction is slightly more complicated in this setting of hard functions to pseudo-random generated. This is completely standard, so let me just write it here in small letters. The reduction R in this setting is allowed to be non-uniform. What do I mean by non-uniform reduction? It means that when R receives oracle access to D, it is also allowed to ask for a short advice string, which depends on both the function f and the adversary D. And it turns out that this is the right notion when you want to study black box proofs from hard functions to pseudo-random generators, and you should trust me on that. I'm not going to go into this in this talk. So now I can state the question that I wanted to ask formally. The question is, does there exist an extreme black box proof? Namely, a black box proof showing that you can start from the extreme high-end imperative weakness on hardness assumption and obtain extreme high-end PRGs. And as I said in the beginning of the talk, we don't know how to answer this problem. This is a great question. But even though we don't know how to answer it, whether there exists such a black box proof or there does not exist such a black box proof, we can rule out certain approaches for coming up with such black box proofs. Okay, so finally, after this long introduction, I get to tell you about our results, which are limitations on some specific approaches for obtaining extreme black box proof. Our first result is that in every black box proof, even one that is not extreme, even the ones that we already know, the construction map E, which is mapping the function f into the candidate pseudo-random generator G sub f, must have certain special properties, which I will explain precisely in the next slide. And we think that these special properties explain why it is hard to come up with new black box proof. It's difficult to come up with constructions with these special properties. But now that we know how they are supposed to look, maybe this will help us to find new constructions, because we know that the ones that we already have by Nissan and Wigderson and by humans and myself cannot succeed in the extreme high end. So if we want constructions that will work in the extreme high end, we need to come up with new construction maps. Let me also point out that these special properties are used to prove the next result. Our second result is that if you use the approach of DEMOS, of the paper that I've told you about earlier, and I'll call this approach the pseudo-entropy generator plus extractor approach, then this approach cannot yield an extreme black box proof. And this explains why DEMOS needed to use additional assumptions, because it's impossible to have a black box proof without using these additional assumptions. And I'll explain this more precisely later on. In our third result, we take a look at the paper of Chen and Tell. They use an approach which I'll call the PRG composition approach. And here the result is less conclusive. What we show is that the pseudo-random generator composition approach cannot yield an extreme black box proof if you use hardness amplification and the hybrid argument. Now, the known constructions in the literature use hardness amplification and the hybrid argument when starting from assumptions like the Impaliazzo-Wigderson hardness assumption. So we think that this explains why the paper of Chen and Tell has to use additional assumptions, has to use one-way functions. But let me just say that, right, as I just said, it doesn't rule out that the PRG composition approach of Chen and Tell can be carried out without the hardness amplification plus the hybrid argument. So maybe this is a place where we can look for a new kind of black box proof. So I'll now elaborate about the three results I told you about. I'll start with the first one, and I want to tell you what are these special properties that the construction map E needs to have. And in order to tell you about these properties, let's view a function f on L bits as its truth table, namely an n equals 2 to the L long bit string. And this allows us to view the construction map E as a map that takes two arguments. It takes the hard function f, which is now an n-bit long string, and a seed x of length far, and it outputs gf of x, what the candidate pseudo-random generator G would have done on the seed x. And the reason I want this notation is because once I define E this way, a classical theorem by Trevisan from '99 shows that black box pseudo-random generators are extractors. namely that every such function E, which is a black box, which is a construction map for a black box proof, is an extractor, meaning that for every high entropy source F over m bit strings, if we apply the extractor on F and an independent random seed, the output is close to uniform. Okay, so what is the special properties that a construction map needs to have? Our result says that every construction map E has the following special property. There is a high entropy source F on which quite a few outputs of E are fixed. And if we examine these two statements, you can see that these two results are at attention, because in an extractor, it can't be that many outputs of E on F are fixed, because this would contradict the fact that the output needs to be close to uniform. So the difference is between quite a few and many. On the one hand, we show that quite a few outputs of E are fixed, whereas it can't be that many outputs are fixed. So the fact that the function E is a construction map for a black box pseudo-random generator is in tension with the fact that it has to be an extractor. Another way of thinking about it is the following result that we have. A random function E is, on the one hand, with high probability an extractor. This is a standard calculation, that a random function E with these parameters is with high probability an extractor. Nevertheless, what we can show is that with high probability, it does not satisfy this special property. So it's not going to be part of a black box proof. And a compact way of saying this is that E must be different than a typical extractor. A construction map E for a black box proof must be different than a typical extractor. And we find it quite surprising, as we tend to think of black box pseudo-random generators and of extractors as similar, whereas it turns out that they need to be quite different, right? In order for a mapping E to be a construction map for a black box proof, it has to be, on the one hand, it needs to be an extractor. This is what Trevisan says. But on the other hand, it needs to be careful not to do too well, right? Because there's a tension between what it has to do and the fact that it is an extractor. Let me say one sentence about the intuition for the proof. And the intuition for the proof is the following. Suppose that E does not have this special property, right? Suppose that E is in fact very different from having this special property. Suppose that when you apply E on a function F that is chosen from the uniform distribution, all the outputs of E on such an F have high entropy. None of them are fixed or even close to being fixed. If this was the case, then I claim that the reduction R will not be able to find such outputs of E because they have high entropy. How can the reduction find them? And since it can't find them, it will not be able to make use of its oracle and will therefore fail. Therefore, since we know that the reduction does not fail in using its oracle to compute F, then it must be the case that at least some outputs, quite a few, have low entropy, and we can fix these outputs without losing too much entropy, reducing the distribution from the uniform distribution to some high entropy source on which quite a few of the outputs are fixed. So this is the intuition for the proof. There are technicalities in making this intuition into a formal proof, but I'm not going to go into these fixes. Let me now elaborate on the second result, that the approach of demos can't yield an extreme black box proof. So let's recall the theorem of demos. Demos show how to construct extreme high-end pseudo-random generators from a qualitatively stronger version of the extreme high-end in Palliatzzo-Wigder's on hardness assumption in which we assume that the function is hard not only against standard circuits, but also against circuits that are equipped with non-determinism and randomness. So that's the result I told you about earlier. How is this result proven? Demos use an approach which I'll call the pseudo-entropy generator plus extractor approach, which was already used in some previous papers. And this approach can be stated as follows. You use the hard function f to construct a pseudo-entropy generator with certain parameters, but I'll explain later. But first, let me explain what a pseudo-entropy generator is. A pseudo-entropy generator is a weak form of a pseudo-random generator, which only guarantees that the output has large computational entropy, rather than guaranteeing that the output is pseudo-random, but it is indistinguishable from random. Instead of being indistinguishable from random, it only guarantees that it has computational entropy, which means that it is indistinguishable from having high entropy, or actually mean entropy. And the approach continues by constructing the final PRG in the following form. You apply the pseudo-entropy generator on a random seed, X. Now the output has computational entropy. And so you extract this computational entropy using an extractor with an additional seed. So a final construction that you get is a pseudo-random generator which takes two seeds, X and Y, applies the pseudo-entropy generator on the first seed, and then applies on an extractor with the second seed to extract the computational entropy and obtain a pseudo-random distribution. Now, the seed length of this final generator is, of course, the sum of the seed lengths of the two objects, the length of X plus the length of Y. Now, we know how long seeds of extractors needs to be. So we know that the second seed, Y, the seed of the extractor, has to be long. It has to be of length almost L. And since we're shooting to construct a pseudo-random generator, which is an extreme high-end pseudo-random generator, in which the seed length is also almost L, 1 plus little o of 1 times L, then the second, then the length of X must be very, very short, right? We've already used all our budget on Y, and we must have that the length of X will be little o of L, right? So this is the approach of Demos. Now, our result is that in every extreme black box proof, in every black box proof from extreme high end in Palazzo-Bigdasson on hardness assumption to pseudo-entropy generators, it must be the case that the length of the seed, the length of X, is large, is almost L, and so it cannot be little o of L. Now, this means that it is impossible to have an extreme black box proof using the pseudo-entropy generator plus extractor approach. So this is the result I told you about. You can't use the approach of Demos to start from the extreme high end in Palazzo-Bigdasson hardness assumption. And since pseudo-entropy generators are closely connected to pseudo-random generators for quantified derandomization, this also implies limitations on pseudo-random generators for quantified derandomization. And I'm not going to say, if you know what quantified derandomization is, then that's great. And if not, I'm not going to go into this more precisely. Let me say a few words about the proof idea. It turns out that the aforementioned special properties of PRGs, that there is a high entropy source on which the output of which quite a few outputs of E are fixed, in fact applies also to PRGs, right? So it also holds for PRGs. And just like we've seen that in the case of PRGs, there's a tension between being a black box PRG and being its information theoretic analog and extractor. In this setting, there is a tension between being a PEG, a pseudo-entropy generator, and its information theoretic analog, which is a condenser, an extractor that only outputs a high mean entropy output. And when the length of the seed X of a PEG is very short, this tension becomes so strong that it is a contradiction, and it's impossible to have black box proofs that have a small length seed, and this is why it follows that the seed length of the PEG must be large, right? So that's the high level of the proof. Let me now tell you about the third result regarding the approach of Chen and Tell. And let's first recall the theorem of Chen and Tell. Chen and Tell show that extreme high-end PRGs follow if you assume the extreme high-end in Palliazzo-Wigderson hardness assumption, but you also need to assume that one-way functions exist. And they use an approach which I'll call the composition approach, namely the generated G is constructed in two steps. You first apply a generated G1 on the seed X, and then you apply a second generated G2 on G1 of X, where, and I'm now going to tell you what are the properties of these two generators. The first generator, G1, starts from the seed length that we want, 1 plus little o of 1 times L, but it doesn't go all the way to an output like 2 to the 1 minus little o of 1 times L that we want. It stops in the middle. It only outputs M1 bits, where M1 is 2 to the omega of L. But when it outputs these M1 bits fool circuits of much larger size, of the size that we do want to fool. So this PRG G1 fools circuits of the size that we do want to fool, but it doesn't output the amount of bits that we want. And it turns out, and this is an observation of Chen and Tell, that such pseudo-random generators can be constructed from the extreme high end in Palliazzo-Wigderson hardness assumption by using the methods that we know how to use, hardness amplification and the hybrid argument, by extending the previous pseudo-random generators. Then the second generator, G2, does the rest of the job. It receives the seed of length M1, right? I mean, the length of the output that we had for the first pseudo-random generator, and it stretches it to the length that we want, to 2 to the minus little o of 1 times L, which in terms of M1 is polynomial in M1. So G2 is a pseudo-random generator with polynomial stretch from M1 bits to M1 to some constant bits. And the way Chen and Tell obtain this pseudo-random generator is that they take this pseudo-random generator as a cryptographic pseudo-random generator that follows from one-way functions. But you should ask, right? Why do they use a cryptographic pseudo-random generator? Why do they need to assume one-way functions? This is a pseudo-random generator with mild stretch, right? With only polynomial stretch. And we've already seen that you can construct pseudo-random generators with almost exponential stretch, assuming in Palliazzo-Wigderson standard assumptions. So where do one-way functions come in? The reason one-way functions come in is that in order to perform the composition, you also need an additional property. And what you need is that the generator G2 should run in time, which is almost linear in its output length. So this is its output length, and it needs to run in time, which is almost linear in that. And the reason that you need this is because when you argue that composition works, then you consider G2 as a potential distinguisher from the point of view of G1. So G2 cannot have size which is larger than 2 to the L. It must have smaller size so that G1 will fool it. But in any case, G2 needs to run in time which is almost linear in its output length. And the known techniques that we use, the hardness amplification plus hybrid argument, do not give pseudo-random generators with these parameters. You can obtain a pseudo-random generator G2 with polynomial stretch, but it doesn't end up running in almost linear time in its output length. So the natural question that you should ask is, is there a black box proof starting from the assumptions that we want to use from the extreme high-end in Palazzo-Wigder's on hardness assumption and constructing a pseudo-random generator like G2, a pseudo-random generator with polynomial stretch that runs in time, which is almost linear in its output length. And our result is that it is impossible for black box proofs to obtain such pseudo-random generators if they use hardness amplification plus the hybrid argument. So this is a weaker result than the one I had on the previous slide. We don't know how to rule out any black box proof of this form, but we do know that if you use hardness amplification plus the hybrid argument, then you can't obtain G2 from the assumption from which we want to start. And let me tell you a couple of things about this result. So this result is essentially showing limitation on black box proofs for hardness amplification in the extreme high end. We are in the extreme high end, and we want to show that, that there's a cost to hardness amplification that prevents you from obtaining a pseudo-random generator that's running almost linear time. And we already have limitations on black box proof for hardness amplification in earlier works. The best previous result is in a paper by Greenberg, Viola, and myself. But that paper and also the previous papers uses techniques that do not work in the extreme high end. They only work in the high end. And the point is that now we want to extend these results to the extreme high end, and we need to come up with a completely different proof technique. And the proof technique builds on earlier works, one by Appelbaum, Hartmenko, Young, and myself, and the second one by Ronsby, Varma, and myself. And what this really amounts to is that you want to prove a lower bound on the number of queries required by locally least decodable code, and along the way, we don't only prove new lower bounds for hardness amplification, but we also proved improved lower bounds on the number of queries required by locally least decodable codes in a certain regime of parameters. So finally, let me conclude and give you some open problems. So this is the summary of the talk, the main question, the answer, and the interpretation. And let me make a comment, and that is that in this talk and in this paper, I focused on pseudo-random generators. But there are other approaches to prove that hard functions imply BPP equals P without pseudo-random generators. And the limitations that I've shown in this talk do not apply for these approaches. And in particular, they do not apply for a very recent paper of Chen and Tel. So if you're only interested in derandomization, not in pseudo-random generators, this may be another avenue in which you can bypass our limitations. So let me now mention some open problems. So of course, the most important open problem is this question. Is there a black box proof showing that if you take a quantitatively properly scaled Palazzo-Wigder's on assumption, namely the extreme high end in Palazzo-Wigder's on assumption, then you can obtain extreme high end pseudo-random generators? And as I've said, we do not know how to solve this problem. More easier and more technical open problems are the following problems. One, the quantitative bound that we get for black box proofs for hardness amplification at the extreme high end, the ones which I just told you about in the previous slide, are not tight. And this is disappointing because in the high end, we do have such tight bound from the work of with Greenberg and Viola. So it would be interesting to extend the bounds that we have in the extreme high end to be tight. A second problem, which is probably much more difficult, is the following. Is the cost of hardness amplification plus hybrid argument necessary for black box proofs for PRGs, right? We don't know how, right? I mean, in the sense that other black box proofs for PRGs, which do better than hardness amplification and the hybrid argument. And in order to attack this problem, we need to develop techniques to prove even very weak bounds on general black box proof for PRGs. Because as you can see in this paper, we were not able to handle general black box proofs for PRGs. We could only handle black box proofs for PRGs which have certain properties, like if they had, if they were the PEG plus extractor approach, or if they were the PRG composition approach. And at this point, we don't know how to prove even very weak bounds against general black box proof for PRGs. So that's it.